Thank you and Sagar for inviting me, and of course the other organizers for inviting me to talk about some of our work on games and networks. Since you have already been through a few lectures of game theory already, I guess some of the stuff I'll be talking about would be just repetition, but I will just go through them because it never hurts to learn or hear about the same thing multiple times. Sometimes it helps to just embed it more deeper into your psyche. But I'll try to go fast over the parts which I think you've already been through. Okay, so just a little flash of what kind of stuff we do on games at the Institute. So we essentially actually started when Sashi, this brilliant PhD student of Deepak Dhar's, came to our institute as a postdoc. And he started talking about a possible alternative to the Nash solution framework called the coaction framework. And so we worked on this, and we in fact found that there were very exciting differences between the way coaction solves some of the social dilemmas like prisoner's dilemma and so on compared to Nash, and it agrees much better with what we know experimentally about these kinds of games. And then he and a wonderful student from IISc, in fact, Apilini Kushal, who's now doing his PhD in the US, worked on minority games and how information and minority games kind of interact with each other to produce resolution to various very practical problems like traffic routing. Then Shakti Shakti is a senior scientist in our group, and he started looking at how games can be used to understand epidemics. And one of the co-organizers of this meeting, Shomik, is in fact instrumental in getting us interested in that, because Shomik came and gave a talk on how you can use games to understand epidemics at more like a mean field level. And so then we started looking into it from a network perspective. And this eventually led to fusion of certain ideas which actually started long back. My first PhD student, Rajkumar Pan, had worked a bit on games on networks or graphs. And Shakti later restarted this whole work looking at how cooperation and community structure of societies can actually co-evolve when you actually play games on graphs. All right, but today we'll be looking primarily on this question of, can we explain the evolution of cooperation or the emergence of cooperation as something what physicists would call a phase transition. So, the science had this special issue in 2005 where they kind of came up with, some 125 questions which they thought were pretty interesting. And of course, in any such list, often the question of why people cooperate comes up. So Elizabeth Pennisi, who kind of wrote this short piece for this particular question in this issue, had said that, this seems like a real puzzle that, when your main goal is to survive and procreate, why should you often take actions which sometimes seem counterintuitive? You'd kind of sacrifice yourself so that others may live. Okay? And we see this, quite often for it to be just, some kind of a random irrational behavior. So to some extent, Halden had tried to answer this by saying that, look, you can understand it by understanding that I will jump into the river to save 2 of my brothers or 8 of my cousins. Can anyone among the students explain why that would be the case? Why is Halden saying that? Yes. Yeah. And cousins share 1/8 and so on, right? And so he's saying that, it's more important, like how much of my genome actually carries over to the next generation rather than, my children in particular. I mean, if I can make sure that, the genomic composition actually carries on to the next generation, I will try to, maximize that kind of. And this, of course, is a very interesting solution to the problem, but unfortunately, this only explains why there will be altruistic behavior among kin. So, for example, if a brother doesn't marry, but spends his life raising the younger siblings and getting them married, you can understand that. But doesn't explain why, when we are not genetically related to someone, why would you go ahead and, do something altruistic, right? And when a physicist kind of starts looking at it, this is often how we transform this. So instead of looking at people, we start looking at simple objects like spins, which are, could be either in an up or a down state. It's kind of farcical, you might say, but sometimes this leads to some very interesting answers. So what we are interested in as physicists into this question is that it's kind of an example of emergence. So emergence has been called, in colloquial terms, more is different, by the physicist Phil Anderson in a very thoughtful paper he wrote in 1972 in Science, and in which he pointed out that when you have lots of components interacting with each other, it gives rise to properties of the system as a whole that don't exist in the components themselves. So where are these properties coming from? So for example, the components could be perfectly rational individuals, people who would be aghast at the thought of hurting anyone, but you put them in a mob and they can engage in the most ghastly of behaviors. Okay? Such incidents are becoming more and more frequent to recount. And the funny part is I've actually personally encountered one of these people who was actually quite proud to be part of a mob that burnt a lot of places down and robbed stuff. But when I talked to him, he was perfectly reasonable individual, and he would not harm a fly, so to say, right? And but somehow when you make him part of a mob, he would go and do unspeakable things. And so the question is if you come to a much more pleasanter aspect of emergence, you can ask how interactions between people who are otherwise extremely selfish, so rational is a code word for people who only would do stuff that will benefit themselves. When they start interacting with each other, it can lead to coordination at the systems level, which we would call cooperation. Okay? So individuals can sometimes forego the benefit of doing it only for themselves so that there is a greater benefit for the collective. So the big puzzle is, why do we do it? Okay? And can we understand it as an emergent property of interacting components? So, so we used to have this physicist in IISc who used to teach any course by saying, or any problem that you took to him, he would start saying, all right, it could be fluid dynamics, it could be, I don't know, something in high energy physics, quantum physics, any problem you took to him, you say, all right, let's not give up. Let's try to map it to the Ising model. So in that, spirit, we often take any problem we actually confront to a system of these interacting binary elements. So, for our purposes, we won't actually care what these are, whether these are magnetic spins or whatever. We are only interested in the fact that these individual entities are capable of being in any one of several mutually exclusive states, the simplest being that they can be in one of two binary state choices. And which state they take up is based on information about what the majority are doing in their local neighborhood. Okay? So for example, one of the simplest cases of Ising model is each agent, in this particular case spin, can be in an up or a down state, or pointing up or pointing down. And they're just looking at their neighborhood. So it could be like 4 nearest neighbor, like front, back, east, left, right. And they're just looking at, what's the majority doing? And whatever is the majority doing, they just follow. So they're like majority rule followers. You can, of course, dress it up as saying it's a ferromagnetic Ising model, right? Or if they're contrarians, if they do exactly opposite of what their neighbors would like to do, you can call it anti-ferromagnetic Ising model. But that doesn't matter to us, right? From the point of view of what we are doing, all that matters is, are they following the majority or are they being contrarians? All right. So in 1944, so there's of course a very interesting history to all of this. So I think last year, sorry, we celebrated the 100 years of Ising model just a couple of years back. And in fact, Parangoma, who's here in the audience, had organized a beautiful conference in Calcutta University on this 100 years of Ising model, where the various ways in which Ising model has been applied to understand various systems across subjects was discussed upon. The funny part is Ernst Ising, this PhD student of Lars Onsager, whose name is forever associated with the Ising model, actually came up with the wrong answer. So, Lars Onsager had asked him, if you take this small tiny magnetic spins and you allow them to interact with each other. Sorry? Sorry, absolutely right. He was Lenz's student. It's the Lenz Ising model. I'm sorry. Yes, I was like just talking about Lars Onsager. Sorry. Thank you for correcting me. Yeah. So Lenz had told him, imagine this tiny magnetic spins, and they're interacting with each other such that each of the spins would like to align with its neighboring spins. So can you figure out what would be the behavior of such a system? And so Ising kind of just worked on a chain of such spins, looked at the one-dimensional system, so to say, figured out that even the tiniest of thermal fluctuations would destroy long-range order, and then just concluded that, okay, maybe this is true for all dimensions. And so it's not very interesting, and gave up. And so it fell to the lot of Lars Onsager, who in 1944, through amazing calculation, showed that instead of a one-dimensional system, if you look at a two-dimensional system where each spin is interacting with its four nearest neighbors, then even for a finite temperature, as long as it's below some critical temperature, you can have long-range order. And so suppose you start with a system which is in this kind of a state, so some are up and some are down. As long as the temperature is less than a critical temperature, then the interactions between them will trump the thermal fluctuations which tend to disrupt the order. And as a result, over time, you would find that the entire system would start getting ordered. So this actually led to a revival of interest in the Ising model. And we now understand, of course, that you can see its collective behavior and as functions of temperature, which can be thought of as some noise which is disturbing the ordering of the system, and an external field. And depending upon the combination of this temperature and the field, you could have a transition from order to disorder. So there are different ways in which order can give rise to disorder. For example, you can have increasing temperature gradually disrupt the order to disorder, or you could actually have a field which causes this order to be suddenly imposed in a particular direction. So for example, if you have a positive field, all the spins are aligned up. If you have a negative field, all the spins are aligned down. And this results in very different kinds of transitions. So if you have a field-induced transition, which is a very sudden transition, so to say, what we call in the language of physics a discontinuous transition, a first-order phase transition, then it's a bit like having a crowd milling in a train station. So everyone is going their own separate ways, and then there's suddenly this public announcement: train number 12607 bound for Chennai is coming to platform number 16, and suddenly you find a collective streaming. Right? Order emerges out of disorder, but there is a stimulus. Okay? On the other hand, there's more interesting kinds of order where there is no such stimulus. Okay, so this is called a self-organized transition, and this is typically what we see when you gradually cool the temperature below the critical temperature, and the system spontaneously organizes itself to have an ordered structure. And the best demonstration of this is something that we used to, as kids, do in Kolkata streets. Now, if you haven't been to Kolkata, there's a very vibrant street culture, and also people who are extremely curious, right? And so we as kids would do this. Like 3 of our friends would come and stand on the street and then stare very hard at the top of the tree. inevitably within 5 minutes, there would be like a few people coming, "Ye cha dada?" Of course, we would be silent or just talk amongst ourselves. And then, more people coming and everybody like intent looking at the top of the tree. And then 10 minutes later, my friends basically backtrack and go away, okay? Leaving this big crowd just watching what's going on at the top of the tree. Okay? So there's nothing going on at the top of the tree, right? There's no stimulus. And yet you have a spontaneous ordering, namely this clustering around the tree. So, can we use these concepts to study cooperation? Of course, objection number one, agents are not particles, they are not spins. Okay, they are not simply responding to external forces inertly. In fact, as one of my economist colleagues puts it very pointedly, that whereas physical entities are guided by past events, strategic agents are guided by the future. Okay. In what sense? Because they are trying to anticipate what's going to happen in the future. Right? And so that's why it's sometimes called teleodynamics, in the sense that they are guided by some future goals. Now, of course, what they are being driven by is their anticipation of what will happen in the future, which itself is going to be some function of their biases, their knowledge of what happened in the past, and so on. So clearly, it's not like it's not tachyonic particles coming and affecting them in any way. Okay, none of that sort. They just have some anticipation of what they expect in the future, and this is what's guiding their action. So how do we study such systems? And so here we switch from spins to games, and what we are looking at are agents which are trying to anticipate what another agent or other agents are going to do. And so, like let's say one agent is thinking, I think I will pick A, but my opponent thinks that I think that I will pick A, so maybe I'll have to figure that into my calculation. Oh, but hold on, she thinks that I think that she thinks that I think that I will pick A. And of course, this endless regress can go on, right? And so the question is, how do you then choose a course of action? How do you get rid of this whole infinite regress business? So for the purpose of the question we're asking, should rational agents cooperate? Here we take the help of game theory. And I'm sure you have already gone through several lectures in which you have told that games are nothing but strategic interaction between agents. And the agents themselves could be anything. They need not be human individuals. They could be cells, they could be organizations, they could even be computer programs. But the important point to note is that each agent receives a payoff which depends not only on the action chosen by that agent, but also by everyone else. And so therefore, in order to maximize your payoff, you need to choose an optimal strategy which takes into account all the information that you have, that other agents have, and your anticipation of what the other agents are going to do to maximize their payoff. And when I say rational, of course, all the time, what I mean is that the agents are only interested in maximizing their own benefit. Any benefit that happens to the collective is just a side effect. Okay? Or, as we say, an emergent behavior. And so we will look at the simplest of these games, the two-person symmetric game. So you have two agents, let's call them A and B, and they can choose between any one of two possible actions. The more perceptive of you will realize where I'm getting at. So in my mind, I have this analogy that just like spin up and spin down, you have two action choices, action 1 and action 2. And, but unlike spin models, here you have payoffs, and these payoffs are such that if the two agents both choose action 1, each of them get a reward payoff. So this is the reward for cooperation. Let's call action 1 cooperation. Whereas action 2 is non-cooperation, a defection, and if they both choose action 2, then they get a penalty payoff, which is the penalization they get for not cooperating. Now, what happens when they do different actions, like action 1 by agent A and action 2 by agent B? So then the agent A gets the succus payoff, S, and the agent B gets the temptation payoff, and exactly the opposite when agent A chooses action 2 and agent B chooses action 1. Now, this may seem like very complicated to you, but just hold on to this and I'll explain what these payoffs mean in a minute. So how do you now decide to choose whether to play action 1 or action 2? You can of course use a pure strategy, which is like you can only choose action 1 or you can only choose action 2. But you can also choose a mixed strategy, which means with a probability p, you choose action 1, and with a probability 1 minus p, you choose action 2. So in those terms, a pure strategy would just correspond to this probability p being either 0 or 1. All right. Now, it turns out that by varying this payoff values or the relative ordering of this payoff values, you can get very different types of games. So for example, if the temptation payoff is the highest payoff, followed by the reward for cooperation, followed by the penalty for mutual defection, followed by the sucker's payoff, you get a famous class of games known as the prisoner's dilemma. On the other hand, if you have reward for cooperation as the highest payoff, followed by temptation for defection, followed by the penalty for mutual defection, followed by sucker's payoff, you get a game known as stag hunt. Now, so what are these games? So let's look at stag hunt. So surprisingly, it turns out that the stag hunt game was proposed as early as 1755 by Rousseau in his book on the inequality of man, where he was basically talking about social situations where people need to cooperate to achieve the best outcome. So stag hunt typically has these two choices that the agents need to make as one, a high-risk strategy having a potentially large reward. So for example, they want, this could be like they're planning to hunt a stag. Now, stag being a large animal requires a lot of people to coordinate their actions to bring it down. Action 2, on the other hand, is a relatively low risk but also poor yield strategy. So for example, hunting for a hare. So you don't need many people to hunt for a hare. You can, as an individual, go out to hunt for a hare. But of course, the amount of meat that you will get is also low. So the question is, if you need to decide whether to go out with several of your friends and hunt for a stag, or to go out for yourself and hunt for a hare, which one will you choose? So here, the reward for cooperation is, of course, that if you cooperate with your friends and all of you manage to bring down a stag, then you get this reward for cooperation, R payoff, which is you feast on the stag. On the other hand, if each of you go your separate ways and each of you get a hare, then of course you get a small meal, proportionately smaller meal. Worst outcome is if one of you goes hunting for a stag and the other goes hunting for a hare. So the person who goes hunting for a stag now actually returns home empty-handed because it's not possible to bring down a stag, singly. And so you return home empty-handed. Right? And the other person goes home with a hare. I mean, okay, he's not as happy as he would have been if he got a stag, but at least he doesn't go empty-handed. Now, you can use the Nash framework for solving this game. So Nash, in colloquial terms, is basically that strategy which, if everyone adapts that strategy, no one will be better off by unilaterally deviating from it. And so it turns out that there are three Nash equilibria for this game. You could cooperate, you could all defect, and these are both pure strategies that also happen to be evolutionary stable strategies, or there could be a mixed strategy which corresponds to some ratio of the payoff values, penalty, reward, and temptation. By contrast, you could have a game where the Nash equilibrium is actually inferior to alternative choices. So for example, if you were not so smart and decided not to go with the Nash equilibrium, you would actually be better off in certain games. And a wonderful example of this game is Prisoner's Dilemma. Now there are many ways you can narrate Prisoner's Dilemma. So one of them is, think of two con men. One is trying to sell diamonds illegally acquired. The other is trying to buy it. And so they go to some dark, shady corner and they quickly exchange suitcases and go back to their respective hiding places. Now, each of them have some temptation to hand the other person an empty suitcase, thinking that, okay, I'm being really smart, I'll get diamonds for nothing or I'll get cash for nothing. Of course, you can work out that if both of you decide to do this, then you'll both return home empty-handed. And so the Nash equilibrium for this game is both should defect. However, if you were not so smart and you didn't know game theory, you would probably cooperate and it would result in high payoffs for both of you, because reward for mutual cooperation is actually better than the penalty payoff for mutual defection. And it looks like that, typically humans do tend to be nicer than what the Nash equilibrium suggests, because several experiments have been tried out which shows that humans tend to be much nicer than what rational game theoretic models would tend to suggest. So what we did was we looked at what happens if instead of having a mean field model of games, you put agents on networks or graphs and allowed agents to only interact with those who are their direct neighbors on this social networks. So this gives rise to bounded rationality, because now agents don't have complete information about everything, but know only about the actions of the agents they're directly connected to. And so now what we are trying to look at is how does the collective behavior arises depend on the type of the game, and so this is given by the payoff matrix, the uncertainty of information about the other's action, and so this is like noise or temperature, and the nature of the connection topology, which is the network. Okay, so we did some early work on epidemics where we showed that in fact you can show that this cooperation between individuals for taking voluntary vaccination changes as you gradually change the source of the information available to you. So inspired by this, we did this where we asked, can the connection topology between the agents itself drive the transition to cooperation? So what we are doing is that each of the agents are playing two-person games with each of their neighbors, and the temptation payoff is a free parameter which governs whether it's going to be a prisoner's dilemma or a stag hunt game. And after doing one round of two-person games with their neighbors, they collect a net payoff, and then they basically decide whether to stick to their current action or change the action based upon a probability which is dependent upon the difference between their current payoff and the payoff of a randomly chosen neighbor. So this is done probabilistically because we say that this is a stochastic version, or where you have some uncertainty about what your agents are doing. However, if this was a deterministic game, then you would just look at your payoff and the payoff of your neighbor, and if your neighbor has got higher payoff, you'll just copy your neighbor, but if you have got a higher payoff, you will stick with what you're doing. All right. So K is like a temperature, which is the measure of the noise in the decision-making process. And what we're doing is we are changing the network in certain cases from being a regular network where you're just talking to people who are your immediate spatial neighbors, to a random network where you can be randomly linked to k other individuals on this system by gradually taking p fraction of these links and randomly rewiring them. So this is the famous small world network paradigm proposed by Watts and Strogatz in 1998. And they argued that this is actually seen in many systems. And what they found is that regular networks are characterized by high clustering and large path length. So, random networks by low clustering and short path length, whereas small world networks are characterized by high clustering, which is a property of a regular network, but short path lengths, which is a characteristic of a random network. So globally they are random, but locally they look like regular networks. And so what we find is that there's a very interesting topological transition which happens, where as we go from regular network to a random network, you find that there are three possible states: all cooperate, all defect, and a fluctuating regime where individuals are intermittently switching between cooperation and defection. So what we find is that so this is temperature, this is the temptation payoff which acts like a field, and this is the phase diagram. So in the regime of the regular network, you find that as the temptation payoff goes from the stag hunt regime to the prisoner's dilemma regime, all cooperate becomes essentially absent. However, if you make it a homogeneous random network, you find that there is a region in the prisoner's dilemma regime, where now all cooperate actually becomes the stable state. And so therefore, simply by altering the connection topology, you can actually promote cooperation in a situation where you wouldn't have seen it otherwise. So let me conclude by just summarizing what we saw, that when played in a spatially extended setting, iterated games like Prisoner's Dilemma or the Stag Hunt provide a wonderful framework for investigating the process of how we make collective decisions under conditions of bounded rationality because of incomplete information. So while the payoff matrices are known and identical for all agents, individuals only have knowledge of the choice of the actions of their neighbors. And as the temptation decreases below the mutual cooperation payoff, the game changes from a prisoner's dilemma to a stag hunt. So remember, prisoner's dilemma is characterized by the unique equilibrium that is given by the dominant strategy of mutual defection, but the stag hunt is characterized by multiple equilibria. And so what we find is the transition between the all defect and all cooperate state is a discontinuous transition, as we saw through looking at finite size scaling. However, the transition from the absorbing states of all defect and all cooperate to the fluctuation regime is a continuous one. In fact, there's a bicritical point where all these three phase boundaries meet. But the most interesting point is that the all cooperate regime actually moves up in this temperature field plane as you increase P, which is basically making the network more random, which can explain why you have complete cooperation in the prisoner's dilemma regime in a random network setting. So I'd like to thank work possible. So Sashi is over here and Shakti is over here. And these are some of the papers that we have published on this. So please feel free to take a look at them. And if you have any questions right now, I'll be happy to answer them. Yeah, sorry, I actually just quickly went over the slide because of lack of time. Good question. So actually, for some reason, this picture didn't come through. So, okay, I'll just explain to you what this is. So there are three collective dynamical states. So there's all C and all D, which are of course absorbing states. But there's also another state, which is a fluctuating state. And this is a steady state, okay, in the sense that it won't settle to either all C or all D. No matter how long you look at it, it will keep fluctuating with individuals switching from C to D, and so on. Okay? So this we can actually numerically check by doing finite size scaling. So for example, we can look at what is the characteristic time that a single individual remains in a cooperating state. And we can see how this, for example, diverges as you go from a all C to a fluctuating state or a all D to a fluctuating state. So you can characterize this as a non-equilibrium steady state. Okay. You can even characterize the critical exponents associated with it. And we found that for at least the case where we are doing parallel updating, that is, we find that these exponents do not belong to the directed percolation university class. Okay. This synchronous updating, yes. A good question. We haven't actually looked at asynchronous updating. There's a possibility that we mentioned in our paper that for asynchronous updating, the exponents might reduce to that of DP, directed percolation, because there are many situations, where if you look at sequential updating, the exponents are DP, but if you look at parallel updating, it's not DP. Yeah. Yeah. You mean how many neighbors? Yeah. No, so the neighbors do affect the phase diagram, but what they don't affect is the basic property that for the regular network, you don't have any all cooperative state in the PD regime. See, this actually corresponds to this dashed line that you see. that divides the stag hunt regime from the PD regime. Okay, so no matter how many neighbors you have, this won't change. What can change is, like, for example, where you come down, where the Aldi state comes down, and so on. Okay, so the basic property that we are trying to pitch here is that regardless of the number of your neighbors, the moment you go, as you go from a regular to a random graph, you have a all C regime which is pushing into the PD regime. So even though it may seem very counterintuitive, how can you actually even have an all cooperating state becoming stable, starting from a mix of cooperators and defectors? By just changing the topology alone, you can actually make an all C regime stable in a certain part of the PD game space. Okay. So this is what I would like to call a topological phase transition. But of course, the name I'm stealing from this Kosterlitz-Thouless transition, where they mean something completely different by a topological transition. But this is also a topological type of topological transition, because all you're doing is you're just changing the connection topology. You're not changing the T, you're not changing the temperature, everything else is kept fixed. Yeah. Thank you. Okay, so what we are doing is actually every individual is playing two-player games with each of their neighbors. Okay, and then they're summing the payoffs. Okay, if you're doing an n-person game, you might want to write down a payoff matrix, which is a separate thing, right? You want to write down like how many players are cooperating, 1, 2, 3, 4, 0, 1, 2, 3, 4, and for each of them you want to write down a payoff. Okay, here we're doing it differently. Here we are saying that each individual is playing a two-person game with each of their neighbors. Okay, and then they're just summing the payoffs. But the action that you take, that is of course unique, because you can't appear as a cooperator for one and defector for another, right? So you're playing a cooperator, let's say, and then with the neighbor who's playing a defector, that defector is going to get a T, and you're going to get a sucker's payoff. Whereas a neighbor who is C, you're going to R, and that neighbor is going to get a R. So depending on how many cooperators and how many defectors you will have some T's, some S's, and some R's. So that's going to be a total payoff. Okay. So at the end of the round, you're basically summing all of this up, and you're asking, is this higher than a particularly randomly chosen neighbor? If it is lower, then I will switch to whatever that neighbor is doing. If it is higher or about the same, then I'll keep doing what I'm doing.
Yeah, but this works, the setting that you said works with the Ising model. Let us say within the restricted boundary.
I mean, it was inspired by the Ising model, but this is also the framework in which Novak and May, for example, looked at their games on lattices. So Novak and May back in the 90s were asking the question, what would happen if you play the prisoner's dilemma game on a lattice? Okay. So what they did was...
1 second.
Yeah.
And then probably you can continue.
Sure.
Assuming that the two prisoners are not communicating, right?
Yes, absolutely. There's no communication.
But then according to the network, you said that each one person will look at make a response based on make an action in response to the other's action, right?
Yeah, no, but the thing is that action is based upon what you eventually collect at the end. So, see, you cannot know what your agents are doing until you already play the game. Okay? So what is happening is the end of the round, you collect all the payoffs, and you find out that you were suckered. Okay? So because you're all surrounded by defectors. Okay? And then you decide to choose to defect in the next round.
Okay, it's the sequential.
It's a sequential game. It's a repeated prisoner's dilemma. It's an iterative prisoner's dilemma. Yes.
Thank you.
Yeah.
So the usual resolution to prisoner's dilemma is given by a sequential game, where you like in the first round you defect and then you see that the other guy is go to cooperation.
Well, it's not obvious. So there are four.
Have a solution in that case, right?
Sorry?
In
No, there are folk theorems which says that you could have cooperation emerge, but it's not clear which one is better. So there are multiple strategies. You could do tit for tat. So then there are these memory one, memory two, memory three, and all these strategies, right? So do you play tit for tat? Do you play Pavlov, and so on? Here we are not looking at those kinds of strategies. We are simply asking that suppose you are just doing copying, okay? So you just copy a randomly chosen neighbor strategy if, or action rather, not strategy, action, if that neighbor's payoff happen to be higher than yours, of course subject to this noise because we are using this probabilistic rule, right? So even sometimes when the neighbor's payoff is lower, you could just by accident choose that particular action, right? So you are just doing copying. Okay? And based upon this copying, we are asking where is the system tending to? So in that sense, it's kind of close to the Ising model analogy, because the only thing that's happening is like you have a field, the temptation payoff, which is kind of deciding which way the bias is going to be, and there's this noise, like which is acting as a fluctuation, and we are saying how by having this interaction between agents through playing repeated games, you are pushing it either to a all C state or to a all D state or to this fluctuation regime. And so we get these phase diagrams accordingly. So that's the connection with the Ising model that I talked about initially. Yeah. No, the network is static. So we fix the network once we have rewired it. It's possible probably to do the network dynamic, but then the question is like, what are we trying to do? So, okay, that's actually no, that's a fascinating question actually. Actually, this thing that I talked, the slide that I showed you first at the very first place where I showed you what are the other things we're doing. So one of the things I said, like this co-evolution of cooperation and communities, that's precisely what we're doing. So there we are saying that suppose you allow people who are interacting, who find out that their neighbors are perennial defectors. They have no incentive to talk to them. So they cut those links and then randomly rewire them with someone else. Okay. So can this drive the system towards a modular network? That is where you have community structures, very tightly bound clusters, which would also be very stable cooperators, because defectors would find it very hard to penetrate those kind of stable cooperator clusters. So that's one of the things where having an evolving or a dynamic network, of course, is very, very meaningful. Sure, absolutely. So we did look at the time required to converge to the absorbing states, like all C or all D. And no, they are all numerical. That's how we got the exponents, for example. So we have this analogy with persistence, or rather susceptibility. The curves look very much like susceptibility curves as you cross the phase boundaries. But I'm not quite sure that's what you are getting at. Yeah, so except that this is very hard to observe it in these kinds of settings, because in a random network, you can't follow, like unlike a lattice. Yeah, unlike a lattice where you can actually look at clusters spatially localized, in a random network, you don't know whether they're connected or not. In fact, so for a long time, we have been trying to understand this question of, is there, how robust is a cluster of cooperators in a random network? But we have always been stumped by this question. It's very hard to track, like defectors, how they're actually, penetrating inside these cooperator clusters because of the topology of the connections. I don't know whether that's connected with the question you asked, but I'll be happy to discuss with you later. Yeah, thanks. Yeah. You mean the fraction of cooperators? No, the fraction of cooperators is maintained. The individuals who are cooperating and defecting will keep changing, but the distribution is fixed. In fact, that's the definition of non-equilibrium steady state. The distribution is invariant.